right, so we're starting vectors. Now remember, we've talked about vectors a little bit. The vectors have direction and magnitude. And we talked a little bit about velocity and acceleration as it related to vectors. But now we need to kind of get into that vector notation. And we've even done a couple of problems that have shown that vector notation. And you've seen it before. It's kind of how we get the distance between 2 points, although we never ever called them a vector. And that was really kind of startling to me when I went back to look at some algebra books and we were looking at how you defined a point and how you defined the distance to the point, but we actually never really used that word vector. So I've started out here with giving you 4 different examples of vectors. They have direction and magnitude. We usually represent them as an arrow. And the magnitude is the length of the vector, but I've got 4 vectors in 4 different places. And we can do it, and we want to deal with some terminology that we're going to utilize. So for example, if I have a vector r, and we can represent it mathematically with this notation, some textbooks will use a bold letter. So you got to kind of watch that as you're going through the textbooks. But now I've got this direction, and if I tell you that it's negative r, it's going to have the same length, but it's in the exact opposite direction. So when we add vectors, what we're doing is we're flipping the direction of a vector if we're subtracting it. And we can represent our vectors in various coordinate systems. And when you think about it, that vector notation, or that our point notation in the Cartesian or polar coordinate systems, really represents a position vector. Where is that point relative to the origin? So we can do it in terms of x, y. We can do it in terms of r theta if we're in the polar coordinates. But what's going to really come into handy, especially when we get into the next chapter where we're talking two-dimensional motion, we want to be able to go back and forth between the 2 coordinate systems, or 2 places where we're going to locate the points. So our next thing is I'm going to actually look at our vectors here, and we can write it out in this notation. So this is kind of our mathematical notation for a vector. We've got it into a point. We've located our point x, y, and we're going to use these little I, j, and k's representing unit vectors. So that's really how they actually mean they're in the direction of the x or the y, and k is going to be for z, but they're going to have a magnitude of 1. And one of the things that we know about vectors is that we can scale them, hence the term scalar. The scalar is going to give us how long it is. So in this case, our vector I has a scalar of x in the x direction and has a scalar of y in the j direction. And again, we talked about how we can convert between the 2 coordinate systems. So if I'm in r and theta, we can use our trigonometry to give us what our x component, or the scalar in our x direction, is. And we can use our trigonometry to give us that y component, or our y scalar in the y direction. And one of the things that we've already learned, or one of the things that you learned back in algebra somewhere along the way, even though we never said that, or at least the textbook that a couple of textbooks that I've seen lately haven't actually used that terminology, we know that we can go back and forth, because this is going to allow us to translate between various systems. And one of the things is our x and y components are independent. How we travel to this point r, so if I'm walking around the block, I can walk x blocks in the x direction and then y blocks in the j direction, or I can do it y blocks in the j direction and x blocks in the x direction, and I'm ultimately going to end up at that same point. So it doesn't really matter about that path. So we've got some vector rules, and we're going to actually see vector rules and develop a whole lot of extra rules as we go through the semester, because we're going to talk about how we're going to manipulate these vectors in terms of what we call a dot or a cross product, or a scalar versus a vector product. But for right now, we're just going to add and subtract, just like what we learned way back in elementary school. We're adding and subtracting things. So one of the first rules is it doesn't matter whether I add A to B or I add B to A. So let's take these two vectors, and these are supposed to represent the two same vectors. So I have a vector A that looks like this, and I have a vector B that looks like that. We add vectors head to tail. So I'm going to add B to A, and I'm going to get a vector AB. I'm going to do the same thing, but I'm going to do it in reverse, just like I talked about walking X blocks and then Y blocks, or walking Y blocks and then X blocks. We're going to be able to get that same resultant vector, A plus B. That's the result of traveling in these two directions. Now, this represents my scalar, right? I can multiply by a scalar, and essentially that I've got A plus A plus A, or I have 3 A's, and I can do that scalar. So you've probably seen this kind of terminology before. So if I'm given a vector A, that looks like a minus 3I plus 6J, and I'm given a vector B, 9I minus 1J, and I want to add A and B. I'm going to add the I components together, and then I'm going to add the J components together to get my resultant vector. Similarly, I can do it with a scalar. So here I've got my A vector, and we're going to subtract 3 B vectors. So I'm multiplying my 3. Now, this was my B vector. So negative 3 times 9 is negative 27. Negative 3 times negative 1 is a plus 3. So I'm going to end up with a resultant vector here. So we can actually do that alphabetical component to it. So to kind of look at this, I want to look at this a little bit in terms of a problem. And we're going to utilize it from just a graphical standpoint, because you can do vectors graphically. You can take a ruler with protractor, and you can actually keep them and scale them, and you can do these things actually with graphs and then just read the length off with the graph, or you can do them mathematically. So I've got a bird. It's going to take a trip, and the first segment of this trip, it's going to fly northwest for 3 miles. It's going to turn, and it's going to fly directly west for 6 miles. Then it's going to turn again and fly southeast for 8 miles. Now, I know it looks like it might say 0.8, but this is actually 8 miles. We want to know what is the displacement from the original starting location. So as I said, it helps that we look at our pictures graphically. And when you're working physics problems with me or anybody, I'm telling you, drawing your picture really helps, because it's going to help you determine, am I in the right track? Does it end up where I think it does? It's going to help me with my positives and my negatives. So I've got my north, south, east, and west, right? And we know that if I'm traveling northwest, my angle is going to be a 45-degree angle, and that's going to come into play here in just a second. But so it said I traveled northwest for 3 miles. Now I didn't do this one to scale, so I just kind of sketched it out. So I'm following along here. And so I went 3 miles to the northwest, then it went 6 miles directly west, and then it went to the southeast for 8 miles. And now I can put on my graph the resulting displacement vector. So we're going to look for vector D. Now, one of the things that this tells us is if I'm in this quadrant, or this quadrant, or this quadrant, or this quadrant, we know what the positive and negatives are. Anything that's in this quadrant, I'm going to be at a positive X and a positive Y. Anything in this quadrant, I'm going to be at a positive Y and a negative X. Anything in this quadrant, I'm going to be a negative X and a negative Y. And in this quadrant, I'm going to have a positive X and a negative Y. So these quadrants really do help us out in terms of how we're going to be working with it. So let's do this mathematically. So we said the first vector, we're traveling 3 miles northwest. And if I'm going northwest, those are 45-degree angles. And that's where my negative comes in, because I'm traveling northwest. I'm going to be in this quadrant, so I better make sure I have a negative value. Now, of course, I could have done my angle from here to there, which would have been 135 degrees, and that would have given me my negative. if I wanted to work it that way. So you've got a couple of ways to work this. And then I've got my 3 in the plus y direction with my 45 degrees. And that goes back here to looking at this. This is where I've got my angle. I could have used, since it's 45 degrees, I could have used that angle. And you're going to be able to convert back and forth between those triangles. So that's why when I talked about the triangle and understanding that right triangle really is very, very helpful and very, very useful. And it's one of our key tools because that's how we're going to convert back and forth between our polar and our Cartesian coordinate systems. So back down here, now we said directly west, 6 miles. That's where the negative sign comes in because I'm going directly west. And then I can do my southeast, and now I'm going to be in this quadrant. And one of the nice things that we're going to learn about vectors is we can slide them around. We can actually move them around to help us out. And as we go into from our general mechanics to our statics to our dynamics, that ability to, as long as we aren't changing its orientation or its length, we can slide it around on the page, really, really helps us out. So I can look at, this one would be headed towards this quadrant here, so I can make sure I have my positives and my negatives correct. So go ahead and do the arithmetic in your calculator, and then we can add up all the x's and we can add up all the y's, and we end up with a vector that's in this quadrant, so it should have a negative and a negative. This gives us a chance to check our signs. Sure enough, we ended up with a negative and a negative. It agrees with our picture. And then we can calculate the magnitude. And we've done this. We've used Pythagorean's theorem for years and years and years, and we can calculate our magnitude. So I'm going to take my x component and I'm going to square it. I'm going to take my y component and I'm going to square it. And I'm going to get 4.31 miles. So the displacement has a magnitude of 4.31 miles. And we can actually write it down here. There's one more step. We can actually determine an angle here. And you're going to use the tangent to be able to determine that angle. And so I'm going to leave that for something for you guys to take that next step. And when you look in your textbook in chapter 3, that really does help. So I want you to kind of look at that, and you can actually find the angle, and that gives us a direction as well. So hopefully this gets you that start on vectors, and we can go from there.